magnets. In this lab, we're going to investigate how the force between two permanent magnets varies with the distance between the magnets. And to do that, we're going to use these cool apparati that Tom machined. So here we have these donut-shaped permanent magnets. These are neodymium, I think N52, which is a really high-grade magnet. So you don't want to let them snap together. So I'm going to put it over here and take the various masses off this brass rod. Here at the bottom we have another identical magnet and a little spacer in case they accidentally touch. It'll be a lot easier to get them apart. And it keeps them from slamming together and shattering. It's dramatic. Everything, the rod and the heavier weights are made of brass, which is a non-ferromagnetic material, and these lighter weights are made of aluminum, same story. So we have various masses here, some brass, they all fit on this rod to keep the magnets, make sure I get it the right way and they don't slam together. So the rod keeps the magnets aligned so that they don't end up flipping around and attracting. Cool. They're a little sticky, so you can, tiny bit of friction, takes some playing with it to get the actual equilibrium position without friction being a factor. A little spin helps. Okay, so the first thing we want to do, if you look at this magnet here, it's being repelled by that magnet, and we want to know how much it weighs. So here we have a normal electronic balance, and because it's electronic, I'll just turn it on there, I don't want to put the magnet right on top. I'm pretty sure we won't get an accurate reading, and it might damage the scale. So my solution here is to get a little spacer to keep the magnet away from the electronics and the metal internal part of the balance. So I'll put this block on, and instead of doing math, which I'll definitely make a mistake on, I'm going to press tear to re-zero the balance with the wood on it, and then put the magnet on top, and hopefully that's far enough away the magnet is from the internal electronics of the scale to get an accurate reading. Let me zoom in here so you can see with your own eyes the reported mass. This is a slow zoom, and the other features of the balance. If you need any other information on there, looks like 11.9 little g grams. Okay, good. Zoom out a little bit. Well, I'll just zoom out a little bit, and I can then get rid of the magnet and the spacer, and I can weigh all our weights that we'll be using one at a time. It probably doesn't weigh a negative amount, so that's a sign that I forgot to tear it again. So back to 0 here. And the smallest weight we have is 10 grams, so on the same order as the magnet itself. We can go through and weigh all the rest, and that'll be included in the data spreadsheet we'll provide. Great, so we're done with balance. That was easy. Now we can go about taking the more interesting data. Make sure everything's in frame. So I'm going to put this magnet back on the rod here and making sure they're still in opposite directions. Yep, they're not going to snap together. Good. Now, well, we have masses, so then we can probably figure out something about the force. the mass of this and the mass of these weights, mass of the magnet, mass of the weights. Then I want to find the distance in between the magnets. So first, for the no added weight, just the weight of the top magnet, I can use a ruler, standard. Well, this one's not quite standard, it bends a little bit, to get the weight in between the magnets. I guess I better zoom in again so you can see a little more clearly what I'm doing here. Actually, I'm just going to bring you over here with me. Great. Okay, so we'll use this one and put the magnet on. Yep, that's repelling. Good. So, the distance between the magnets, here's my ruler again, and I could do between the bottoms of the magnets, from the outsides, from the insides, or some point in between. I think from the inside edges is going to be the easiest to measure, so it gives us a good line to see. And I want to make sure that friction's not stopping this anywhere other than the true equilibrium. Try to minimize the friction effect. Looks like 5.5 centimeters, 55 millimeters. We have another cool tool. We're sort of limited in that we're dealing with magnets. We can't use all our fun metal equipment, but I do have a micrometer here that could allow us to get a bit more precise of a measurement possibly. Let's try that. If you know how to read a micrometer, it's a trick to it, but I'm sure you could find a tutorial somewhere, although I'm not quite getting to the bottom here. They might need some more finagling. If anyone has any ideas, let me know and I'll take some more data. Oops, I don't want to move it. So inches is on the side closer to the setup, centimeters is on the other side. I'm actually moving it when I try to get a good read here, so maybe that needs some more playing with. Maybe I need to move this magnet up a little bit. So that looks like 55, and then we're going to look for the next line that matches a line on the other side. And from this sort of awkward angle where I'm showing you, could be the 7. Maybe more like 57 millimeters. Or that'd be 55.7 millimeters. 55, should get a smaller pointer than my fat finger. And then the 7 is the one that lines up next. That's a little introduction to micrometers. And then we can go through and add weight. Add the smallest weight. And so that's the weight of the magnet plus, or the mass of the magnet plus the mass of this aluminum disc that we weighed, and measure the new separation, either with the ruler or however we decide to do it. And work all the way up to, this is the biggest mass we have, about 500 grams. We could add that, do that by itself or with all the other cumulative weight to get a really small separation. It's going to be challenging to get in there to measure. So we may actually, in this case, want to measure from the outside of the two magnets, which is a lot easier to see here. So if we take that number, then we'll have to just subtract the width of each of the magnets in between, which I can do here. get this out of the way so you can see it. So this will definitely work for finding the width of the magnet. And it looks like it's about, a little pencil to point it out, 0.56 millimeters, and then the next line that lines up perfectly looks like the 4. So I would say 6.4 millimeters is the width of one of these permanent magnets, or 0.64 centimeters. Sound good? Well, that's all the measurements I can think of right now. Let me know if you want me to try something different, and we'll see what we can do.